Okay, so in this video, I'm doing 3 first examples of derivatives. And specifically what I'm going to do is I'm going to fill in this table. We have 3 functions, the function x squared, the function square root of x, and the function 1 over x. And we're going to go through the same story for each of them to discover what is their derivative and what that means, sort of starting with nothing and using limits to get to where we want to go. So what is this going to look like? I also, for each function, have a little Desmos thing. So here's the function x squared, here's the function square root of x, and here is the function 1 over x. And we're going to tell the same story for each function, and then we're going to do some algebra to get exactly what's going on with each function. But to start with, let's do the function x squared first. Here it is. And we're going to have some point of interest that we can vary by sliding it around on Desmos. So the Desmos links are included. I encourage you to go click on it. You can click on this little point and you can drag it around. And that is our point of interest on the function. And the nice thing about functions is if you zoom in enough, so if you zoom in around one point enough, the point of interest, the function will eventually kind of look like a straight line. And when it looks like a straight line, you might ask yourself, what is the slope of that line? If you can figure that out, you can kind of approximate the function really well. So that's what we're going to try to do. But let's zoom out again. And how are we going to do that? We are going to use the secant line. So if you go over to here to the folder called secant line and you click this button, the secant line should appear. So here is the secant line. And what we've done is we've taken our point of interest as one of the 2 points on a secant line, and we are looking at the other point as being some distance h away. So the distance between this dotted blue line and this dotted orange line is the distance h. So let's, for convenience, let's take the point of interest to be at x equal 1. And now let's look at this secant line, which is distance 1 away. So it's going from 1 to 2. That orange line is the secant line. It cuts through the function f. And in this case, it has a slope of 3. And that slope of 3 is not a great approximation to the blue curve, right? The slope of 3 is kind of cutting through a function that's not doing that well. But as we shrink down the interval on the secant line, which again you can do by dragging, you can see that the secant line, that orange line, is getting closer and closer to the actual function near the point of interest. And as you do that, Desmos is calculating the slope of the secant line as you go. So as you get closer and closer, the slope of the secant line, it starts out at 3, it goes down here to 2.5, 2.2, 2.1, and as you get closer and closer to 0, you shrink that interval down to almost nothing. Something really exciting happens right when you get to the final point, which is that it's undefined. The slope of the secant line is undefined right when you get to the very place we want it to get to, which is sort of an interval of size 0. And the reason is because the secant line, to find its slope, you need 2 points. If you set the slope to 0, you set this h value to 0. That's the h value is the difference between the 2 points. If you set that to 0, you have a divide by 0 error. You have a 0 over 0. You're trying to find the slope through 1 point repeated twice. The rise is 0, the run is 0. So finding the slope doesn't work right there. So the way to get around this is to do the limit of the slope of the secant line. So instead of looking at what is the actual value when h equals 0, just think about h getting closer and closer to 0 forever. This is the idea of the limit. And you can see here it's getting really close to the value 2. So the tangent line is going to capture this idea. That is going to have a slope of exactly 2, and that is going to be the limit of the secant lines. So as the secant lines get closer and closer to our original point, we reach this limit, which gives us the slope of the tangent line. So even though the slope of the secant line is undefined, by taking its limit, we got 2, which is the slope of the tangent line. And you can play this game. You can do this whole story of the secant line. You can do it at any point of interest you want. So we're going to start out by doing it at 1. In this case, the value was 2. And then we are going to see what happens when you move the point of interest around. So I don't know, maybe you're interested in the point 1.5. And you shrink the slope of the secant line, you get the slope of the tangent line. In this case, it's 2.94. Let's do 1.5 exactly and see what we get. Then you get, it's getting closer and closer to 3. And you can play this game anywhere you want. You can slide this to some, let's say, some negative value. Let's do -1. And okay. And this whole thing with the secant line, we can play the game one more time. as the secant line shrinks down to 0, as the length of that little cutting segment goes down to 0, the slope of the secant line gets closer and closer to the slope of the tangent line. Let's make this -1. So even though the slope of the secant line is undefined, we can calculate its limit, and it's going to be -2. And you can do this for every point. So at every single point, you can calculate the slope of the tangent line, and that value, that result, is called the derivative function. So if you click on this folder, derivative function over here in Desmos, it will show you this purple function. And this purple function is plotting the values of the slope of the tangent line as you vary the point of interest. So at our original point 1, when we were exactly at 1, the slope of the tangent line was 2. So this function, this purple function, which is going to capture the value of the slope of the tangent line, is 2. And then at 1.5, we said it was 3. At -1, it was -2. And at -1.5, it's -3. So you get this nice purple function that tells you the slope of the tangent line at any point of interest you want. And that is what I call the three-part story of what is the derivative function. So we start out with the original function, just the original function. We have the point of interest. And then the first part of the story, we compute what is going on for the secant line. We calculate the slope of the secant line for any h value. In the second part, we calculate the limit as h goes to 0, and we calculate the tangent slope. We can calculate the slope of the tangent line at any point. And then, by thinking of how this changes, this tangent line, how it changes as you change the point of interest, we get this new purple function, the derivative function, and we can find a formula for that. So that's what we're going to fill in on our table. And so that's why our table has 3 rows for each of these 3 steps. And each of these 3 steps is going to have an interpretation with slopes. That's what I gave. So the first step is going to be the slope of the secant line. Slope of the secant line. That's going to be the first line. And we're going to have this h value that's going to tell us the difference that we're looking at. So from x to x plus h, where the h value is how far apart the points are, and x is our point of interest. So that was this orange line in Desmos. So we're doing step 1 now. It's going to be the secant line, and here it is. So there's the thing, and okay. All right, back to licks here. This slope of the secant line has 2 other ways you can interpret it. One is as a rate of change, and in this case, it's the average rate of change from x to x plus h. And that average rate of change has this nice formula of rise over run, which is simply f of x plus h minus f of x. That's how much the rise is, how much the y values changed. And that will all be divided by, oh boy, divided by the run. And the run is just h, because that's how far apart things are. Okay, let me make this average. Let me see if I can fit this on 2 lines. Average rate of change. There we go. From x to x plus h. This is also sometimes called the difference quotient. Or sometimes just the dq. So there's the formula for the dq for any function f. In our particular function, it's going to be this thing, which is x plus h squared minus x squared, all divided by h. That's the difference quotient. And we're going to do it for the function x squared first. Once we have figured out what this is, by doing the limit, we are going to find the slope of the tangent line. And to be concrete, we're going to do it at a particular point, x equals 1. We're going to find that out. In our case, we know already the answer from Desmos. We know the answer was 2. The slope was 2. So we're going to figure out that the slope was 2. So once again, if the point of interest is at 1, and you take this secant line and you shrink down the interval, it's getting closer and closer to 2. And if you actually plot the tangent line, it has a slope of exactly 2. So that's what we're going to fill in on our table. And then we're going to see, as you change the point of interest, how does this thing change to get that purple function, which plots the slope of the tangent line for any given x value. And it turns out this purple function is the function 2x. It's the function 2x. So it's the function 2x. Okay, so the slope of the tangent line at x equals 1, and the slope of the tangent line for any x value is going to be 2x. These things have names. The other name for this thing is the derivative function, sometimes called f prime of x. And this thing that we figured out, the slope of the tangent line at x equals 1, it doesn't have a specific name. You would call it the value of the derivative at 1, right? So the value of the derivative f prime of x tells you the derivative at any x. If you're doing it at x equals 1, you're plugging in 1 for the derivative function. So sometimes people could say this, the derivative at x equals 1, or something like that. The interpretation of this is not the average rate of change, but instead the instantaneous rate of change of the function at x equals 1, and the instantaneous rate of change for any x value. Okay, so this is what we're going to fill in. These are the formulas in general for any f. We're going to do it specifically for this x squared function, and I have 3 steps. One where we figure out the difference quotient, one where we find the derivative at x equals 1, the slope of the tangent line, and one where we find it for any x value. And then we're going to repeat the same thing once we do it for x squared. We're going to repeat the story for square root of x and 1 over x and see if we can find the pattern that is common among these 3 things. So step 1, this is the secant line formula. Maybe I should say slope of the secant line. Slope of the secant line. And it's always this rise over run formula. This rise over run formula always works. And in our case, it looks like this. X plus h squared minus x squared divided by h. And that formula will always work. But the problem with this formula, as we saw in Desmos, is that when h is equal to 0, you'll have a divide by 0. And in fact, you have a type 0 over 0 badness. When h equals 0, the top is x squared minus x squared is 0, and the bottom is 0. So we would like to try to simplify away this badness and hope that this helps us find the limit of 2 when h goes to 0. So to do this, in this particular case, I'm going to notice difference of squares. Difference of squares. So I notice a difference of squares in the top of this fraction. And what do you get? You have the difference of squares, x plus h minus x. That's one of the 2 terms. And then you have the same thing, but with a plus sign on the top there, plus x. And this is all divided by h. And this is becoming a difference of squares because you have something squared minus something else squared. Well, it's the first thing minus the second thing times the first thing plus the second thing. So it's exactly as I have it written here. And you can simplify this a little bit more. In this one, you have an x and then you have a minus x. That just becomes an h. So the nice thing about doing math on the computer is you can copy paste, and then when you simplify, you can cancel the terms. So here's an x and here's a minus x. Those just cancel out. I can delete this. I can delete that. We're left with a plus h from that first square bracket over here. In the second square bracket, I have an x and then I have another x. So I have altogether, I have 2x, and I can cancel this one out. So that's what we have. And now we notice even more cancellations because over here I have an h, and here I'm dividing by h. So those cancel out, and we're left with just 2x plus h. So the difference quotient, the slope of the secant line, and that was from x to x plus h, that is this nice formula, 2x plus h. So I'm going to simplify it in my table instead of writing it out in this way. Let me see if I can zoom out so we can find everything. Okay, there we go. Now we can fit everything on the screen at once. So we did the slope of the secant line from x to x plus h, and it's generically this formula, but we simplified the formula in this case to get the very nice formula, just 2x plus h. Beautiful formula, nice and simple, and there's no problem with it. Before, originally, if you write it out this way, this thing is not defined at h equals 0. So it's hard to do any kind of operation with it when h is getting close to 0. Now it looks like this. And now it's very simple. So, and we can see there's going to be a relationship. We can already see the pattern that's going to develop to give us these numbers 2 and 2x. But that's what we're going to do to get step 2. We're going to do the limit of the slope. Let's say the limit of step 1. Yeah. So again, step 1 is the slope of the secant line, but it has these other interpretations as the average rate of change, or what people call the difference quotient, the change in the y values divided by the change in the x values. Step 2 is doing the limit when x equals 1. The limit when x equals 1. And which limit is it? It's the limit as h goes to 0. It's the limit where the secant line, the difference between the 2 points, that h value, how far over you go to get from the blue line to the orange line, that is going to 0. So it's this limit where you shrink in from here and you shrink. What is the limit of that? Okay. So this is, in our terminology, this is the limit as h goes to 0 of the dq, of the difference quotient, or in our case, it's the limit as h goes to 0 of 2x plus h. And the nice thing about all the work we did in step 1, simplifying this down, is now that work pays off because 2x plus h is a formula where you can just plug in because it's continuous. Just plug in because continuous. Oh, and I apologize. It's not 2x plus h. We're doing the case when x equals 1. 2 times 1 plus h. So it's the limit of 2 plus h, and the limit of 2 plus h, when you plug in h equals 0, which you can do because this is a polynomial, you get 2 plus 0. So the answer is 2 plus 0, also known as 2. And that is why we have just explained why in Desmos, when you look around the point of interest of 1, oh boy, when you look around the point of interest of 1 and you shrink this secant line all the way down, you get, in the limit, you're getting closer and closer to a slope of 2. So even though the secant line would be undefined there, the limit of the secant line, which is this tangent line, that is what the orange line is getting closer and closer to that red line, and that red line has a slope of 2. That is what we have just figured out. Okay. That was step 2, figuring out the value of the derivative at x equals 1, the slope of the tangent line at x equals 1, or equivalently, what is called the instantaneous rate of change of the function at x equals 1. And again, the nice reason this is so valuable is that if you zoom in enough, if you zoom in on this point of interest, the function looks almost like that red tangent line there. The function in blue is indistinguishable from the tangent line as long as you're kind of zoomed in enough. And that is very useful for approximating what's going on with the function. So even though the blue function is complicated, we can approximate it by this simple red line. Okay, the next step, step 3, is to take what we did at x equals 1 and generalize it to any x value. So by sliding around where we're starting, not just at x equals 1, but at x equals 2, at x equals 0.5, at x equals -1, and writing down the slope at all these places, we can make a new function which keeps track of the slope, right? So here at x equals -2, the tangent slope is -4, so the value of this new function is -4. That's why it's all the way negative over here. And here, the tangent slope is -2, so the value of the function is -2, and so on. And you can see that this purple function captures the slope of the tangent line everywhere. It turns out this thing has a slope, the value of this function is 2x. Why is it 2x? That's what we're about to show in step 3. And it's exactly what we did before. We're doing the limit as h goes to 0 of step 1 for an arbitrary x, for any x. Okay. And again, we're kind of assuming we know how to do limits because we do already. So we're doing the limit of the difference quotient, and it's the limit as h goes to 0 of what is the function now. And you have to be careful because it depends on x and h. But the limit that we're doing is only when h is going to 0. So x, just leave it alone. It's just some number, and we're only worried about the x's. Or sorry, the h's. The h's are the only thing that's changing. So in this case, just like before, we can just plug in because it's continuous. So just plug in, and maybe I could say h equals 0 text. And that's totally okay because I say 2x plus h, if you want to be very technical, you'd say is continuous in h. So thinking of it as a function of only the h values, it is continuous in the h values. And that's why it's okay to just plug in the value h equals 0. And if you do that, you get 2x plus 0. So wherever we saw an h, we plugged in h equals 0, what the limit was going towards, and we got 2x. And that is 2x. Okay, 2x plus 0 is just 2x. And that explains why, in our table, we got that the slope of the tangent line was 2x. And that explains why, in Desmos, this purple function is a line with slope 2, and this purple function captures the slope of the tangent line anywhere. Okay, so that is the full story and the full table for the function x squared. Now that we know the story and the 3 parts, step 1, step 2, step 3, we can repeat the same story for the square root function. And we're going to have to use a different trick to simplify it. So here we use difference of squares. We're going to have to use a different trick for square root of x. But we will get to the entry here. And if you look carefully, there's a pattern between x squared and square root of x. So let's do the same thing, but for the square root function. And I made a whole other Desmos for this. Of course, it looks exactly the same. Same kind of thing. So we put the secant line up here and we see what is happening. We see 0.4, so here is the slope, 0.44, 0.45. The secant lines in this case, the slope of them seem to be getting closer and closer. 0.496, 0.498, 0.499, undefined. So just like before, the slope of the secant line itself is undefined at h equals 0, but we can figure out what it's getting close to by simplifying with algebra. And in this case, it's going to get close to a tangent line, which has slope 1/2 at 1. And once we've done that, so that'll be step 1. Once we've done that, we can move around the tangent line and see how that changes as we change the point of interest. But let's do step 1 first. So the secant line, we're trying to show that the secant line is getting close to 1/2. Let's do that. And that is filling in this entry of the table. What is the average rate of change of the square root function? So generically, what is always true is you can always write it as the square root of x plus h minus the square root of x divided by h. So it's the original function. You plug in x plus h, you plug in x. That gives you the rise, right, in our secant line here, right? We have these 2 points. Here's the f value at x. Here's the f value at x plus h. You subtract them. That gives you the rise. And the run is h. So that's what it is generically. But can we simplify it to make this 0 over 0 problem go away? So that's what we're going to do over here. In step 1, we're going to find the slope of the secant line like we did. Okay, so we start out with this formula, which I'm going to copy paste in. And this is what people would write as the dq, the difference quotient, is this much. How are we going to simplify this? And in this case, we're going to use another trick that we saw when we did limits. We have 2 square roots. We are going to multiply by the conjugate. Okay. Multiply by the conjugate. And when you multiply by the conjugate in this case, what does it look like? I'm going to copy this guy in. The conjugate is some other fraction that we multiply by. And what I'm going to do is every time I see a square root, the square root of something minus something, I'm going to replace the minuses with plus signs. So I'm going to replace this minus with a plus sign. That's kind of the conjugate. And to make sure I'm not changing the fraction, I'm going to put that both in the numerator and the denominator. So this whole fraction over here is just 1. So I'm taking what I originally had. I'm multiplying it by 1. I haven't changed it at all. But by introducing this plus sign, I have forced a difference of squares to appear. So in our last problem, there was a difference of squares. But now, by multiplying by the conjugate, I've created a difference of squares. So what do you get? You have this guy. This guy. I just want the top. Let me see. The thing on top, something minus something else, times the first something plus the something else. That altogether will be a difference of squares and will become square root of x plus h all squared minus the square root of x all squared. Okay, that's on top. The denominator some kind of horrible mess, but never mind. We'll just copy and paste it. Yeah, let's copy and paste it rather than typing it out. Here's the denominator. So there's an h, and then there should also be these terms. Okay, so that's what it is by using difference of squares on the top. Things simplify a bit because I got a square root sign and a squared sign. So those simplify. And we can just get rid of those. And we have the same thing over here, a square root sign that cancels out with a squared sign. Okay, actually, let's to be nice, let's put those back. And then let me copy and paste the whole line so that this intermediate step survives in our final document. Okay. We have this, okay. And we said this guy becomes, this goes away, that goes away, the 2 goes away, beautiful. This goes away, that goes away, that goes away. Okay, and last cancellation, we got an x, and then we have a minus x. So that's nice. That cancels 2. X and minus x, those go away. And oh my goodness, there's an h on the top and an h on the bottom. This is what is causing the 0 over 0. When you plug in h equals 0, you would get some kind of 0 over 0 problem. But because these perfectly cancel out so nicely, I could just cancel them out just like that and be left with this really nice final formula, 1 over the square root of x plus h plus the square root of x. Okay, and let me put that in our table. Instead of our ugly expression, I have a nicer expression. And by simplifying it, we have gotten an expression that makes sense when h equals 0. And it was just some algebra steps, in particular this trick of multiplying by the conjugate to get us there. But now we've done step 1, and we've basically figured out how to find the secant slope for any x value and any h value. Now what we're going to do, step 2, is see what is the limit when the secant line, when the secant shrinks down to nothing, what is the limit of that slope? And that's step 2. So step 2, the limit of h goes to 0 of step 1 when x equals 1. And just like before, all the hard work we did is going to pay off because it's going to be a just plug in limit. So we're going to do the limit as h goes to 0 of the dq, which is the limit as h goes to 0 of this whole thing. Okay. And this is a just plug in limit. It's continuous in h. And oh, I did the same mistake I made before. We're doing x equals 1. So every time I see an x, just replace it with 1. We're doing the limit when x equals 1. You can just plug in. Just plug in. Okay. You can just plug in. And when you just plug in, you get. So every time I see an h, I just replace it with a 0. The square root of 1 plus 0 is just 1. This whole thing is just equal to a half. It's equal to a half. 1 over the square root of 1 plus 1. The whole thing is just a half. So great, I figured out this value is a half through this algebraic means. And we can double check that this makes sense in Desmos. Is the slope getting closer and closer to a half? Is the tangent line slope a half? Yes, it is, 0.5. So perfect. So we figured out the slope of the tangent line when x equals 1 was exactly a half. Let me go back to x equals 1 exactly, okay? And now the question is, how is it changing? How does this tangent line slope depend on x? So we can do step 3 now, which is the limit as h goes to 0 for any x value when x is anything, and same kind of limit. There's no problem in this limit. In fact, let me just copy the whole thing and just change. Okay, let's just copy the first line. Okay, so it was x plus h plus x, right? This was the formula that we came up with in step 1, and now we're doing the limit as h goes to 0. And like before, just leave the x's alone. We're just plugging in. Just plug in h equals 0, right? That's what we're doing. H equals 0. That's what we are doing. And it's okay because it's a continuous function of h. There's no 0 over 0 problem or anything like that. So all our work with limits pays off now because we know this technology of just plugging in. And what do you get? You get the square root of x plus 0 plus the square root of x. And the square root of x plus 0 divided by the square root of x, also known as 1 over 2 square root of x. Very nice function 1 over 2 times the square root of x. Okay. Alrighty. So let me fill this in on our table. Oh, we got to fill it in math mode. Okay, there we go. 1 over 2 times the square root of x. And we can double check that we're right if in Desmos, what we could do is we could plot the function y equals 1 over 2 square root of x, which looks like this. Let's make this function purple. And is it true that the values of the purple function are matching the slopes of the tangent line? So is the value of the purple function a half here? And it looks like it's exactly 1/2. That's great. Okay, so that's good. At x equals 2, the tangent line slope is 0.35. What is the value of the function? 0.3536. There you go. So that worked well. And at x equals 4, say, the tangent line slope is 0.25, looks like, if you get it right on. Is this 0.25? Yes, it is. So this function, 1 over 2 square root of x, seems to match perfectly. And in fact, if you just turn on derivative function, you will get the whole purple line exactly as we had it. It's the function 1 over 2 square root of x. And the values of that purple function tell you the slope of the tangent line at any point, no matter what. Okay. So great, we did the function x squared first, then we repeated the same 3-step story for square root of x. And you might notice a pattern here. The value, the instantaneous rate of change at x equals 1, was 2, and then it was a half. And this should get your creative juices flowing, because the square root of x is actually the same as x to the power 1/2. So this was 2, x to the power 2. This was a half, x to the power half. Will the pattern continue for the function 1 over x? 1 over x is x to the power minus 1. Will this pattern continue? So let's do the function 1 over x. And I have, again, a third Desmos file for 1 over x. And we're going to repeat the same 3-step story. So we're going to start with the secant line. We're going to shrink the secant line down to nothing, see what the slope becomes as you get closer and closer to that original point, and this as the secant shrinks. And we're going to use that to figure out the slope of the tangent line. And once we get the slope of the tangent line, we can see how that varies. That will be the derivative function. So let's see how that works for 1 over x. So same 3-step process as we've done twice now. So step 1, slope of the secant line. Okay, and so we're going to calculate the dq. The dq is always this ratio. If I can get my commands right. F of x plus h minus f of x divided by h. It's always that. Rise over run for the points x to x plus h. In our particular case, it's the function 1 over x. So we're looking at f of x plus h is the same as just 1 over x plus h, right? That's the function f. F of x is 1 over x. So that's our dq. It is this little guy. How are we going to simplify this? Well, this is just fraction math. We've got to do, we have a bunch of fractions that we have to deal with. How do you subtract two fractions? You find a common denominator. So I'm going to common denominator them. Common denominator. And when you common denominator them, you get something. What do you get? Let's copy and paste the whole thing over. And then I will do the common denominator. So to do a common denominator between x and x plus h, I'm going to multiply the top and the bottom here by x, multiply the top and the bottom here by x plus h. So there's my common denominator of x plus h times x. And now I can subtract these two things. Okay. So here we go. I guess let me start by copying it. Okay. X minus x plus h, right? I've combined the two fractions now. So there you go. That's what we got. This is all very nice, but I have a fraction divided by h. Why don't I simplify that down by doing what? Let me just write it as one single fraction dividing by h. You might as well shove that h into the denominator. So those two things are equal. You can take the fraction and then divide it by h, or you can just put the h in the denominator. That's exactly the same thing. So there's my fraction. And now, same miracle that happened twice already. You know, I'm starting to suspect there's a pattern here, and it's not a miracle. We have an x, and then we have a minus x. So those cancel out. You just replace the x and the minus x. Those cancel away. In this case, the minus sign on the outside of the bracket is multiplying this whole bracket. So minus plus h is the same as minus h. So those two things are equal. Be careful with that minus sign. And last but not least, the same miracle that happened twice already happens again. H on the top, h on the bottom. What is left over after you cancel those out is this very nice number. 1 over x times x plus h. Don't forget that minus sign. So we're going to copy this over. That was the whole algebra we had to do. And we're going to copy this over to get the difference quotient. Minus 1 over x times x plus h. And because we did all the hard work of simplifying it here, all these steps to simplify it, to get rid of the h over h, which was causing a 0 over 0, now step 2 and step 3 are a breeze. So at x equals 1, limit h goes to 0 at x equals 1. What will that be? It'll be the limit as h goes to 0 of the difference quotient, which will be the limit as h goes to 0 of this formula when x equals 1. So let me finally get it right at the beginning. We're plugging in x equals 1. What's that limit? It's a perfectly good limit in terms of h. And we can just plug in, just as before. Just plug in h equals 0 because it's a continuous function. And when you plug in, you get this very nice answer. Minus 1 over 1 times 1 plus 0, which is minus 1. Minus 1. So we did all the hard work to simplify. We just plugged in h equals 0 to get minus 1. So the answer in our table, the slope is minus 1. Does it match what is going on in Desmos? Is the slope minus 1 here? Yes, the tangent slope is minus 1. And you can see that the secant line really does, when it shrinks down to 0, the slopes are getting closer and closer to minus 1. So they start out minus 0.5, but they're going minus 0.6, minus 0.7, minus 0.8, minus 0.999. And so even though the slope of the secant line is undefined right at h equals 0, you can approach it, and you find that limit of minus 1. Okay, so we did that. Last but not least, can we figure out what is going on for any value of x, right? That's step 3. So that is, when we move this point around, how does the slope change depending on the point of interest, right? Can we figure that out? Before we do that, let's point out something cool. The pattern worked, right? X equals 2, x squared was 2, x to the power 1/2 was a half, x to the power minus 1 was minus 1. Does this pattern hold forever? The answer is, let me spoil it. The answer is yes, the pattern works forever. So let's add a column. If you do x to any power, so it could be x cubed, x to the 4, any power you want. Let's call it x to the power p. The formula will always be, so this will actually be quite nasty. I won't fill that in, but it will be true that this is p. So if you have x cubed, the slope will be 3. If you have x4, the slope will be 4. The slope at x equals 1 is always the power that you started with. Better question, what is the derivative function? Can we figure this out? What is the derivative function here? Okay, let's see if we can do it for x's this column. And if we can do that, we can maybe guess the pattern. And that's step 3. Here, the limit as h goes to 0 for any x value. And the nice thing is, again, you just have to do the limit of the dq. Let's write it out. h to 0 of the difference quotient. And that's this formula. The difference quotient we said was this. So it's the limit h goes to 0 of this, which is the limit as h goes to 0. We can just plug in. Just plug in h equals 0. So again, don't get confused by the difference between the x's and the h's. The x's are just hanging out. It's the h that matters. And in this case, we're going h goes to 0. We can just plug in. And what do you get? You get the limit of, let me copy this whole thing out. Every time you see an h, you replace it with a 0. Minus 1 over x times x plus 0, also known as minus 1 over x squared. Minus 1 over x squared. So that is the formula over here that you get by just taking the difference quotient and by doing the limit. That's the same as plugging in h equals 0 here. And you get this nice formula. Minus 1 over x squared. What is the pattern here? Can we fill in the pattern for a generic p? Let's see if we can do it. So, okay, first of all, let's check that this was right on Desmos. Getting ahead of myself. So we don't need the secant line anymore. We're on step 3 here. How is this tangent line changing as we change the point of interest? And we can plot the derivative function minus 1 over x squared looks like this purple function. And you can see it's always negative. This tangent line is always pointing down. So on this part of the function, it's pointing down. On that part of the function, it's always pointing down. And you can see that's really steep over here because the purple function is really, really negative, right? The purple function goes all the way down here. And it's really steep over here, again, but it kind of mellows out when you get to big x values. So when you get to big x values, that purple function is quite flat, and the slope is negative 0.05, slopes that are close to 0 as you get out of here. So it all works perfectly well, as you would expect from doing the formulas with algebra. Okay, so last but not least, let's see if we can guess the pattern here. So here, x squared became 2x. X to the 1/2 square root of x became, after doing this derivative process, 1 over 2 square root x, which you could write as follows, as a half times x to the power minus a half, right? Dividing by square root of x is the same as an x to the power negative 1/2. The half is a square root, and the minus means dividing. This thing that we just did is minus 1, right? This slope at this minus 1, and then times x to the power minus 2, right? Dividing by x squared is an x to the minus 2. So what is the pattern? How are we doing this? X squared became 2x. X to the 1/2 became 1/2 x to the minus 1/2. And x to the minus 1 became minus 1 times x to the minus 2. So the p is always in front. P is always in front. Whatever the power is always the first coefficient, 2 or a half or minus 1. And it's always an x to the power something, x to the power something, and the something is always 1 less than whatever we started with. So the power of 2 became a power of 1, x to the power, this is the same as 2 times x to the power 1. The power 1/2 became a power minus a half. The power negative 1 became a power minus 2. 2 times x to the power minus 2 here. In general, if you start with a power p and you subtract 1, you get p to the power minus 1. And it turns out that this is perfectly true. If you start out with x to the power p and you do this whole process in general, you will always get this formula for the derivative function. P times x to the p minus 1. This is sometimes called the power rule. So I will add this to the title, and the power rule for derivatives, which has this fun flavor of the p jumping down and then subtracting 1. We're going to see that when you do derivatives, most of the time you don't do this long, laborious 3-step process. You just do that when you're learning what derivatives are, and for your first few examples. Most of the time you learn these rules, like the power rule that says the derivative of x to the p is p times x to the p minus 1. And by using those rules, you can get very complicated derivatives. Okay, that's going to be it for this video. I hope these 3 Desmos things help you out. I hope this table helps you understand what's going on. And yeah, going forward, we're going to be learning more rules like this power rule and learning how to do more and more complicated derivatives, not by doing the limits every time, but by just skipping, finding the pattern, and someone is going to tell us the pattern. We're going to skip all the hard work and just learn what is the final answer. And then we're going to learn how to use them to do interesting calculations. Okay, I'll stop there.